Hello everyone. In this session, we are going to solve the questions which are helpful for the competitive exams. We are taking a subject power system. This is the question number 1. Which of the following methods used for maintaining the voltage within limits are provided at both ends of transmission lines? Option A, static wire compensators at heavy loads. Option B, shunt reactors. Option C, shunt capacitor banks. Option D, synchronous condensers. If we read the question carefully, here they have mentioned a transmission line. For transmission line, there is a problem of over voltage or under voltage. As we are aware that for EHV line, so more than 220 kV volt transmission line, there is a problem of over voltage, especially during the light load condition, during the night hours. The voltage at the receiving end trying to be more. So in order to reduce that voltage, we need to use a device so that can absorb the reactive power. So therefore we need to use a shunt reactors. Why there is a problem of over voltage, especially during no load or light load condition? Because in a transmission line there is a presence of capacitors which are distributed throughout the line length. Due to the presence of capacitor during no load condition, capacitor supplies more reactive power, therefore voltage will be more, and in order to minimize that voltage we need to use the shunt reactors at both ends. They have mentioned that at both ends which device we need to use. Now shunt capacitor banks, where this is used, so this is used to improve the voltage. So whenever we want to improve the voltage, we need to use this particular shunt capacitors. Static wire compensators is a new technology, a FACS technology, flexible AC transmission system and device, and it is also used especially to improve the voltage. And in most of the distribution sites we use the shunt capacitor banks, where there is a chances of lower voltage or under voltage. In order to improve that voltage, we use the shunt capacitor banks. In transmission also, in 220 kV or below 220 kV, we use the shunt capacitor banks. But in general, for all the EHV transmission line, at both ends there is a presence of shunt reactor in order to reduce the Ferranti effect. Okay, so Ferranti effect is a phenomena in which the voltage at the receiving end is more than the voltage at the sending end due to the presence of shunt capacitors. So next question. So to find the most accurate value of resistance and inductance of the transmission line, option A, end condenser configuration is used. Option B, pi configuration is used. Option C, T configuration is used. Option D, distributed configuration is used. So here very important what they have mentioned, that most accurate value. So here value. So we need to determine the most accurate value of the line parameters R, L, C and G. For that various configurations are used. Out of these first three, that is end condenser, pi configuration and T configuration, these are called as the lumped parameter module, whereas this one is the distributed parameter module. So what is the difference between lumped and distributed? In case of lumped parameter, we assume that the various values like R, L, C, G, they are present only at few locations. So it is called as a lumped parameter module, and it is the approximate module. So in order to simplify our calculations, we are assuming that they are present only at few locations, that is the lumped parameter, and accuracy of this method is low. So this is having low accuracy, so accuracy is low. Whereas most accurate method will be the distributed configuration method, where we are assuming that all the line parameters R, L, C, G are present throughout the line length, so they are distributed. If you see the diagram of each, so end condenser configuration, so how we can represent? So here there is a presence of R, L, so we are assuming the capacitors to be present only at the receiving end or at the load end. So this is the end condenser or end capacitor module. Condenser is nothing but the capacitor. So R, L, C, this one is our load. So this is the receiving end, this is the sending end. So this one is our first, that is the end condenser configuration. What about nominal pi? So in nominal pi method, so series parameters R, L are assumed at the middle, whereas the shunt parameters, that is the capacitor, they are assumed, half of the capacitor is assumed to be present at the sending end and half is assumed to be present at the receiving end. So this is C by 2, this one is C by 2. So this is R, X. So this is our nominal pi method. This is the end condenser method. Now option C is T configuration, that is nominal T configuration. So here what we are assuming that half of the series parameters are situated at the sending end and half are situated at the receiving end. So here this is the nominal T method. This one is the load or the receiving end. So Z by 2 is present at the sending end, Z by 2 present at the receiving end, and here there is a presence of capacitor C. So this is called as a nominal T method. Now option D is the distributed configuration where all these parameters R, L, C and G, they are assumed to be distributed. So R, L, C, G. Again after some time at next line length we can have again R, L, C, G and so on. So this is the distributed. Again at the receiving end we will have R, L, C, G and so on. So this is quite complicated method but most accurate method, and here there is a sending. So here this particular method is known as a distributed configuration. All the parameters are distributed throughout the line length, whereas here we are assuming the parameters to be lumped, to be present only at few locations. So more accurate is the distributed configuration. Now suppose if this option is not mentioned, option A, B, C are mentioned and let us say option D is none of these, then out of these three most accurate will be nominal pi. So that also you remember, out of these three most accurate is nominal pi, among these four most accurate is the distributed configuration. So question number 3, the capacitance and inductance per unit length of a 3-phase line operating at 110 kV are 0.01 microfarad and 2.5 millihenry. The surge impedance of line is. Now what is the expression for surge impedance? ZC. So it is the square root of L by C. So this formula we should remember. So this is equal to under root. Now how much is the L? L is given as 2.5 millihenry. So 2.5 into 10 raised to minus 3 divided by C, which is 0.01 into 10 raised to minus 6 as it is in microfarad. So if we simplify this, so 2.5 we can write as 25 into 10 raised to minus 1 into 10 raised to minus 3, that is 25 into 10 raised to minus 4 divided by, this is 10 raised to minus 2 into 10 raised to minus 6, that is 10 raised to minus 8. So if we write, so this will be 25 into 10 raised to minus 4 into this 10 raised to 8. So this will be equal to under root 25 into 10 raised to 8, 10 raised to minus 4, it will be 10 raised to 4. If you take the square root, root of 25 is 5, root of 10 raised to 4 is 10 raised to 2. So this will be equal to 500. So what is the correct answer? Correct answer will be 500 ohm, and remember the surge impedance, it is a resistive quantity, so it will have a unit of ohm. Okay, practice how to do the calculations without using the calculator, because in most of the exams virtual calculator will not be provided unless it is a gate exam. So therefore practice this. So next, question number 4. A string insulator having 4 units, 33.33% of voltage of the total voltage is across the bottommost unit, its string efficiency is. Now to which insulator this particular question is asked? So it is basically on the suspension type insulator. So it has a 4 units. So if you see, so this is our tower, then cross arm, and here there are 4 units. So we know that each disc will form a capacitor. So here there is a conductor. Two type of capacitors exist. One is the self capacitor represented as C, and another is shunt capacitance between tower and a insulator pin, that is the shunt capacitance C1, and C1 is related to C as C1 is K times C, and we know that value of C1 is smaller as compared to value of C. Now this voltage is V1, voltage across the second unit is V2, third unit is V3, and the last unit is V4. The total voltage is V, which is the line to neutral voltage or phase voltage, and string efficiency, we know the formula, it is the voltage across the whole string divided by number of disc. In this case, number of disc are 4 into voltage across the disc which is nearest to the conductor. So the disc which is nearest to the conductor has the voltage V4. Now what they have mentioned, that 33.33% of voltage, that is 33.33% of V, is across the bottommost unit. So we can put here, so numerator V as it is, this is 4, and V4 is 33.33%, that is 0.33 of V. So how much is the string efficiency, that we need to calculate. As it is in percentage, we need to multiply by 100. So this V and V, it will get cancelled. Now in order to simplify this, what we can do, so this 100 as it is divided by 4, so 0.33 is nothing but 1 by 3. So 1 by 3 is 0.33. So this 3 will come in numerator, so that is 300 divided by 4, that is 4 7s are 28, 4 5s are 20. So correct answer will be 75%. Remember, string efficiency is always less than 100% because we will not have the uniform voltage distribution across each disk unless the system is DC. If the same question is asked for DC, how much is the string efficiency of a DC system? Suppose this is the question, then answer will be 100%, because in case of DC system, the voltage across each disk, it will be uniform and we will have 100% string efficiency. So question number 5. Corona usually occurs when the electrostatic stress in the air around the conductor succeeds. Option A, 30 kV maximum value per centimeter, 22 kV per centimeter, 11 kV per centimeter, 6.6 kV per centimeter. We know that the corona effect takes place in a power system due to the partial discharge of air surrounding the conductor. In order to happen that, the electric field intensity E, it should exceed 30 kV per centimeter maximum. So this is the figure. Now this is the maximum value. In terms of RMS, if it is asked, then E should be equal to 30 divided by root 2 kV per centimeter. So that comes to be around 21.21 kV per centimeter in terms of RMS. Now here it is asked regarding the maximum value. So correct answer or correct option will be option A. Coming to the next question, question number 6. If delta is the loss angle of the power cable, its power factor is. Now we know that we can represent a power cable by parallel RC circuit. So resistance and capacitor in parallel. So it will have a voltage across it as V, resistance R, capacitor C, current flowing through the resistor, let us say it is IR, current through the capacitor is IC, total current supplied to the cable is I. In order to determine this particular power factor, we can draw the phasor diagram. So while drawing the phasor diagram, we can take V as a reference. Now voltage across R and C, it is V as they are connected in parallel, and we know that current flowing through the resistance is in phase with the voltage. So if we indicate the current, then current we can indicate in same phase. So this is the current flowing through the resistor IR. So current flowing through the capacitor IC leads the voltage by 90 degree. So we can draw IC like this. So this is IC. And if we calculate I, so here I is nothing but the phasor sum of IR and IC. So IR plus IC. So if we add IR and IC like this, so this side it will be the total current I. Now we know that the angle between the supply voltage and current is phi, but they are asking in terms of delta. Now what is delta here? So delta is this angle. So this particular angle, it is nothing but the delta. That is the loss angle of cable. Now what is the relation between delta and phi? So here we can easily see phi is 90 minus delta. So this total angle is delta. So phi will be 90 minus delta. What is asked? Asked is the power factor. So cos phi, so that will be equal to cos of 90 minus delta. What is cos 90 minus delta? It is sin delta. So the power factor of a cable in terms of loss angle, it will be sine delta. So correct option will be option B. Coming to the next question, question number 7. Choose the incorrect statement with respect to DC transmission system. Option A, this question is regarding DC. It has less corona loss and reduced interference with communication circuits. So that is correct. In case of DC system, corona loss is less and also the interference, radio interference, it is less with the communication circuit. Option B, the potential stress on the insulation is less in case of DC system than that in case of an AC system for the same working voltage. That is also correct. So this option is also correct. So electrical power can be generated at high DC voltage for DC transmission. Here what they are written is we can generate high DC voltage, which is not true. We cannot generate high DC voltage. It is always better to generate high AC voltage, okay, because of the commutation problem. So therefore we cannot generate the high DC voltage. So the wrong statement is this. That is the correct option for this question will be option C. If we see the option D, there is no skin effect in the transmission line in DC transmission system. That is also correct, because as you know that in case of DC there is no presence of inductance. Therefore current will be uniformly distributed throughout the surface. So option A, B, D are correct statements. We have asked the incorrect statement. So correct answer will be option C. Now coming to the next question number 8. The sag of the transmission line was found to be 2 meter when there is span of 100 meter. This is the question on sag of a line between the two level of supports without any change in other conditions. If the length of span is only increased to 120 meter, what will be the new sag? So what they are telling is that in the first case, when length L1 is 100 meter, sag S1 is 2 meter. Now if the length is made 120 meter, then how much will be the sag? So that is the question. We know that for equal level of support, here they have not mentioned equal or unequal level. So we can assume the equal level of support by default. So for equal level of supports, sag S is given by W L square by 80. So here W is the weight of conductor per unit length, L is the span length between the two towers, T is the tension in the conductor. So S is the sag. Now here what we can observe from this, so they have told that only length is changed. Okay, only length is changed. So if we assume W and T as constant, so sag is directly proportional to L square. So what we can write? We can write, so sag in second case S2 divided by S1 will be equal to L2 square by L1 square. That is equal to L2 by L1 whole square. So therefore we can write S2 as S1 into L2 by L1 whole square. So how much is S1? The original sag is 2, new length is 120, the old length is 100 square. 0, 0 will get cancelled. Now whenever we are solving this without calculator, what we can do usually, we can little bit simplify this. So 12 by 10 into 12 by 10. So here what we can write, or directly also we can write 12 square is 144 into 2. 144 into 2 will be 288 divided by 10 square will be 100. So that will be easy. So it is 2.88. So correct answer it will be 2.88. So remember, the sag is directly proportional to length. So this relation we should know. From that we can easily determine. Moving to the next question, question number 9. A 25 bus power system has 5 generator buses. So total buses are 25 and 20 load buses. For the load flow analysis using Newton-Raphson method in polar coordinates, the size of Jacobian matrix is. As we are aware that there are different methods of load flow analysis like Gauss-Seidel load flow, Newton-Raphson, fast decoupled and so on. Now Newton-Raphson is one of the common method of carrying out the load flow analysis in a power system. Now we should remember the relation or the size of the matrix, size of Jacobian matrix. So we should remember this size of Jacobian matrix in case of NR method, Newton-Raphson method is given by 2n minus m minus 2 by 2n minus m minus 2. Okay, so number of rows will be 2n minus m minus 2 and number of columns will be 2n minus m minus 2. So what is n here? So n is nothing but the number of buses, so total buses, and m is the number of PV buses. Number of PV buses, PV bus, or it is also known as a generator bus. Here we should remember, here we should exclude the slack bus, excluding slack bus, because slack bus in every system we take one bus as a slack bus and we should not include the slack bus as a PV bus, because slack bus will be 1. Okay, irrespective of total number of buses, slack bus is always 1. Okay, now here how much is n? So if we read the data, 25 bus power system, so total number of buses are 25. It has 5 generator bus and 20 load bus. Now here total generator buses are 5, remaining 20 buses are load bus. So here m, shall we take 5? The answer is no, because m is number of PV bus. So m, it will be total generator buses are 5, out of that 1 will be slack bus. So 5 minus 1, that will be equal to 4. So m is equal to 4. Number of generator bus excluding slack bus. So one bus will be slack bus. So here slack bus, it will be 1, PV bus, it will be 4, and load bus, it will be, how much is the load bus? It will be 20. 4 plus 1, 5, total are 25, so load bus will be 20. Now what will be the size then? So 2n minus m minus 2, so that is 2 into 25 minus m minus 4 minus 2, okay, by 2 into 25 minus 4 minus 2. So it will be 50 minus 4 minus 2. So that is 50 minus 6. That will be 44 by 44. So size of Jacobian matrix will be 44 by 44. So correct answer will be option D. Okay, so remember this particular relation, the size of Jacobian matrix. So from this we have calculated. And one more important thing is, here we should exclude the slack bus while calculating the number of PV buses, that is the value of m. Moving to the next question, question number 10. Which of the following is not an advantage of interconnected electrical grid system? So we know that our grid system is interconnected. So option A, the grid system can improve the diversity factor of each generating station connected to the grid, which is quite true, which is the main advantage of using a grid or interconnected system, that we can increase the diversity factor. Because more is the diversity factor, the peak load of various generators will occur at different instant, and therefore the total peak load, it will be reduced, or our curve, it will get flattened, load curve will get flattened. That is the correct, it is actually the advantage. Next, the grid covers a smaller number of consumers than that of an individual generating station, which is not correct, because whenever we have an interconnected system, each generator will cater its own load. Okay, so therefore this option is wrong. What is asked, which is not an advantage. So option B is not the advantage. We will check the next two. The arrangement can exchange the peak load of a plant. That is absolutely correct. It is a big advantage of interconnected system. We can exchange the peak load. Therefore we require a smaller reserve capacity for each generator because of the load sharing. Option D, the interconnected grid increases the reliability. That is also very important advantage, that due to the interconnected system, even if we want to take the maintenance, or even if there is some problem in any of the generator, the remaining generator can supply the load. Okay, so the not advantage is option B. The correct option will be option B. Next, question number 11. Which of the following is not valid advantage of bundled conductor? So what is bundled conductor? Using more than one conductor per phase is known as bundled conductor. For example, if we use two subconductors per phase, so this is our R phase, this is Y phase, this is B phase. This is an example of bundled conductor. Sometimes we can have three like this in triangular configuration, R, Y and B. So all these three will form the R phase, these three will form the Y phase, these three will form the B phase. Likewise, we can have 4, 6 or 8. Okay, here just for example, I have shown two configurations. Now what is the main advantage of bundled conductor is that if you see the inductance which is given by L equal to mu naught upon 2 pi ln natural log mutual GMD, geometric mean distance, divided by self GMD. So this is the expression for line inductance, okay, Henry per meter. Likewise the capacitance C is 2 pi epsilon 0 upon natural log mutual GMD by self GMD. Mutual GMD by self GMD. Okay, so these two expressions we should remember. Now whenever we use the bundled conductor, overall self GMD, overall diameter, it will increase, that is self GMD will increase. Now if self GMD increases, mutual GMD will remain same, because even if you use only one conductor, then also distance between the adjacent phases is same, and even if you use the bundled conductor, it is not much difference to have the adjacent distance between the conductors, so mutual GMD is same. So if self GMD is increased, what will happen to inductance? It will reduce. And here in case of capacitance, if self GMD is increased, overall denominator will decrease, that is capacitance will increase. So due to the bundled conductor, L will reduce. So if L reduces, XL, that is the reactance which is given by 2 pi FL, it will also reduce. Capacitance, it will increase. And also with the due to increase in self GMD, corona effect, it will reduce. And if corona effect reduces, radio interference with the transmission line, with the communication line, radio interference with the communication line, it will reduce. At the same time, power transfer capability is increased. Power transfer capability is increased with the help of bundled conductor. Why? Because power transfer capability, you are aware, if we have the sending end voltage as Vs, receiving end voltage as Vr, it is given by Vs Vr by X sin delta. So if your X is getting reduced, power transfer capability it will be increased. Okay, so these are all the advantages of bundled conductor. So here which is the not valid advantage? So reduced reactance is valid. Reduced voltage gradient, that is also correct. So voltage gradient G is inversely proportional to the self GMD, or we can say the diameter D. So more is the conductor size, because overall size is getting increased. So if size is getting increased, potential gradient will obviously reduce. That's why corona is reduced. That's why reduced radio interference is reduced. So this is correct. Reduced corona loss, that is also correct. Increased reactance, which is not correct. Okay, and it is asked which is not the valid advantage. So correct answer will be option D. Okay, so here we have solved 11 questions on power system. I hope practicing these questions will increase your confidence, and also whenever we are solving the question, we are going through the various concepts associated with. For example, here 5 to 6 different type of questions can be formed only on bundled conductor. So therefore always it is a good practice to practice questions, okay, in order to do the more sound knowledge of the concepts. Thank you.